Okay, so let me get started. So the plan now is to go further into this next part of the class we started last time. So last time I kind of gave a little bit of a start on the story about the free particle, and it was more try to give it a slightly unusual motivation you wouldn't normally see in a physics class, which was that that this is really fundamentally, in quantum mechanics, you have a fundamental idea about time translation, and that's the Hamiltonian operator in the energy. That if you want to, when you start talking about a free particle, what you're really talking about is you're adding in a notion of space, and you're adding in the notion, and the crucial thing is space translations and symmetry under space translations. So what this kind of means is that from the point of view of representation theory, you're introducing a new operator, the momentum operator, and then the kind of physics input was that the relationship between energy and momentum be kind of the standard thing that you knew about from classical mechanics. But what I want to do today is to go start telling you a lot more about the about the free particle, and especially today, what I want to do is maybe give kind of a survey and more of an introduction into the analysis, because what's happening is that in typical physics classes, you're talking about functions. You say we're going to describe this free particle by some kind of function, but you never really kind of come to grips very much with the question of exactly what functions you want to talk about. And for good reason, because there's a lot of, this is where you get into a lot of the trickier mathematics of analysis. So what I want to do today is explain some of that, to go over what the Fourier transform is, and to explain some of the subtleties of analysis, and how to think about which kind of functions you want to deal with. And I also should recommend, so I realize here I can recommend a source that has more details about the Fourier transform, about some of the analysis, which is the notes. So I've uploaded it to the files part of the courseworks, and it's also there's a link on the web page for the class. But basically, last semester when I taught Fourier analysis, partly because COVID had hit, I thought it would be a good idea to actually write up some fairly detailed notes. And so those notes have a lot more about some of the topics I'll talk about today, especially about distributions. So if you want to see a bit more about what a distribution really is, I can recommend those notes. But but to start, I think maybe the first, maybe kind of explain kind of what the problem is, why we have a problem. So here's the let me see. The main source of the problem is that, so last time what the idea was that we wanted to take as our state space functions on R. So this is the state space at a given time, and you'll also, this states in here will then also depend on time. But this R is going to be just space. So mostly for quite a while, I'll just be talking about one dimension of space. Physically you've got 3 dimensions, but nothing very interesting happens going from 1 to 3 dimensions until we get to stuff about rotations, a lot of which you already saw. Let's see. So last time we did. Okay, and so then the question is, and what we saw. Well, so the question is which functions. Okay, so if I say I have a function space, I want to know which functions. And now the usual, the obvious answer, or anyway, what the obvious answer is that we want to we want to use the fact that that transformations are unitary, and we want to study inner products in this space, because those are going to tell us, by Born's rule, those are going to tell us what the probabilities of things happening are. So we need so what we want to a standard thing to do is to look at functions with finite norm. So in other words, so remember we're gonna work that there's kind of the standard inner product on these things, which is to integrate f bar, and I'll try and consistently use q as the variable for a spatial dimension, and then f r of q, g of q, q. Okay. So you just give these the standard inner product, and then you say that L2 of R is the function set of functions f with f squared, which is f is finite. Okay. So what you want to do is look for things with finite norm, and then you're going to have the inner products between these things are going to be finite, and you're going to have a nice anyway, and you can use the general quantum mechanics formulas and Born's rule nicely. But there's problems with this. Okay, and then maybe one comment about this is that exactly what this means depends upon your theory of integration. And if you take so normally for what you're doing in physics, you just use a standard. This is just a standard Riemann integral. If you've taken a more advanced math classes, you'll see that you can make sense of the of these integrals for more general functions by going to a fancier version of the integral, which has nicer properties, called the Lebesgue integral. But that's not that's not important for what I'm trying to say here. That you might want to anyway. So you have to think a little bit about what you mean by the integral. But this is kind of the standard thing to use. But then there's problems. There's kind of two. There's problems with this, and the first problem is that what we said that in the when I looked at this and we looked at the momentum operator, that you wanted to find that the irreducible reps, which are on one-dimensional spaces of functions on e to the I, what do I call it again, k q, are not in L2. Okay, so these functions are not things with finite norm. And if you calculate the integral of the size of this thing squared, you're integrating one from minus infinity to infinity. So these things have infinite norm in this standard norm. So your problem is that you if you've decided that I'm going to take the state space to be these L2 functions, and you've decided I want to think in terms of representation theory, and I want to think in terms of representations of the translation group, then the irreducible representations are not actually in the space. So this leads to all sorts of troubles and confusion. And then the second problem is that if you take you would also like to be able to, the momentum operator acting on the space you find is basically just differentiation with respect to Q. And the problem is that the so P and H don't preserve L2. Okay. So you've got this is so I mean, if somebody hands you a nice state and you start acting on it with these operators that you have, it may take you, even if the initial state has a finite norm, if you take the derivative, you may know that the derivative may no longer have a finite norm. And same thing with the derivative squared over 2m also may not have a finite norm. So if you look at most a lot of books that try and do the mathematics of this more carefully, one thing that they'll do, so they have troubles dealing with this, but you'll often find some long discussion of the fact that you're trying to use L2 of R, but you're having to continually check everything that you do, whether you're whether the operators that whether the things that you're using are in the domain of the operators that you want to use, or the domain in range, whether these operators are preserving the things you want to do. So these are the problems with this kind of standard physically motivated choice of using finite norm functions. Okay, so this is just kind of set the stage of why we have to do something. We can't just kind of go ahead with this. Okay, so what to do? Well, here's the one tactic. So one idea. And so this is something you'll often see again in physicists at some point often do this. Is what you want to do is sometimes compactify and is replace. Look at periodic functions. Period L. And L. Then later take. Okay. So the idea is instead of trying to do something on the whole real number line, just work on the real number line with opposite sides identified. So if you like on the circle, so just look at functions on the circle, and so you consider functions on S1, and for now I'll start by writing down formulas assuming that that L is equal to 2 pi, that it's a standard circle with radius 1. But then at the end you'll see what you would need to do to take L to infinity. And now this is just let's see. So I'm going to do this very quickly because this in some sense is the thing that was the first problem on your problem set was to use what you knew about U1 symmetry to deal with the fact that functions on the circle had this U1 symmetry, and you have a nice basis. So the irrefs of the U1 rotations, just these e to the how do I want to do this? Yeah, just these e to the I, and let's call it phi, I guess I called it. And then what you could do, so what you do is you write any function as see how am I doing this? Okay. And then you can write any function functions on S1 as using this basis. And so you had f of phi equal to the sum of a sub n e. Okay. Right. And so here then. Okay, so the thing which I asked you about on the test was more asking about the doing this for actually maybe let me write this. I'll write it this way. So well it's let me write it this way. So it's a sum from n is equal to sum minus n to n a sub n. Fine. And then and then you're later you want to take n goes to infinity. Okay, but you can kind of reduce this to this nice finite problem of just looking at functions that have this kind of finite expansion in terms of this nice basis. And here on the circle, you don't have this problem with the basis elements given by the irreducible representations of translations being non-normalizable. So these e to the I n phi are perfectly normalizable on the circle. The problem is only going to happen as you take the size of the circle to infinity. That's when you're just going to start to get a problem. And there's just some standard. Let's see, how did I want to do this? Yeah. So. Okay. Okay, and then there's just a standard. The a sub n are often written as f hat of n. They're written as they're the so-called Fourier coefficients, and there's a formula for these things that you can easily derive. It's 1/2 pi, the integral from minus pi to pi of phi e to the minus pi. Okay, and then what you find when you do this is you find okay. So this is just the standard, the so-called theory of Fourier series. You're going back and forth, but you can go back and forth between functions on the circle, and then functions on the integers, which are the Fourier coefficients of the function. And then you can write, and then these two formulas tell you how to go back and forth. But this is all kind of based upon the fact that you've got a really nice basis for the functions of the circle given by these irreducible these things which behave, which transform into themselves when you do a rotation. Okay, and then the only kind of analysis here. So then L2 of S1 then goes to so the condition for a function here to be in L2 to be square integral corresponds to a condition on these guys that the sum over n that the a how does it go that the sum over n n goes to infinity. I think okay. So you have some kind of condition on these Fourier coefficients that they have to fall off. Anyway, they have to be square summable, and there's so in some sense on the Fourier coefficient side, there's also a nice notion of what the norm squared is. It's this, and things that have a and this Fourier transformation process is kind of a unitary thing. It takes the norm here to this norm here, and you've got and things having a finite L2 norm this way. It means that they have a finite norm like this. So this is just there's a much longer story about Fourier series and about convergence and everything. But in the first problem that we talked about kind of is kind of automatically solved and it isn't there. you have to worry a little bit about your you know, as long as you add some extra condition, like you don't deal with discontinuous things, or you put some other condition, you can. Anyway, let's just say that you get rid of the first problem pretty much completely, and you can do that. Okay.
Isn't so an isomorphism between L2Z and L2R? So could you sort of go back to the R case like this, but it would look slightly different?
No. So yeah. So the problem. So yeah. So this is well, this is isomorphism between. So this is L2 of S1, and this space is sometimes called small L2 of Z. That these are functions on Z, but we're not. There's nothing here about this. None of this tells us anything about L2 of R yet.
Okay. Isn't that isomorphic to L2 of R, like as a Hilbert space? Are they both countable dimensional Hilbert spaces?
Well, isomorphic. I guess there's some sense in which all Hilbert spaces are the same, but I don't want. I don't. Yeah, I don't. Yeah, but that's kind of much too. That's kind of much too abstract. That doesn't. That kind of isomorphism doesn't preserve any of the structures that we are going to use. So yeah, you can't get away with that. Yeah.
We're only using this one to calculate convergence. We're not using it for any sort of calculations.
Wait, excuse me? What?
We're only using this one to test convergence. We're not using it for sort of calculations or anything.
Well, I think you're trying to invoke some very general theorem about kind of functional analysis, and I'm just saying that at that level at that level of generality, where if you go to high enough level of generality where you don't see any real difference between L2 of S1 and L2 of R, you're missing a lot of the crucial things that we're going to find crucial. And like for instance, everything about fall off at infinity behavior. So yeah, I'm not sure what I'm trying. Yeah. Anyway, I think you're asking me to get into some kind of abstraction, which is not going to, which is not a good idea for this question. Okay. I don't know. Sorry, I don't know if that's much of an answer.
No, that's okay.
Okay. But anyway, so right now the only thing I wanted you to take from this is just that this. So doing this is also what physicists you'll often see them refer to this as putting the problem in a box. That what they've done is instead of having, because there really is all sorts of kind of physical and conceptual and mathematical problems associated with worrying about what happens as you go off to infinity and what happens as you go off to infinity in different directions. Well, if you get rid of infinity and just put it in a box, then you get that's similar. That's essentially the same as imposing periodic boundary conditions, and then you get a much more straightforward setup. And it really is just that you don't have to worry about what happens as you go off to plus or minus infinity, and which we're going to start worrying about in a minute. But you don't have. And then even better, the other and in physics you sometimes will also call this an infrared cutoff. That if you've got that you're putting some kind of restriction that I'm only going to consider degrees of freedom in some kind of finite range, and that's called putting in an infrared cutoff. If you furthermore try and avoid the problem of dealing with the possible that these infinite sequences here and just stick to finite n, that's going to be called that's going to be putting some kind of restriction on how you deal with not having to deal with what's happening at really short distances. That's called an ultraviolet cutoff. So this is just kind of intended as if you want to avoid analysis, these are or get rid of some difficult analytic problems. These are the things you can do. You can kind of get rid of the long distance problems, and sometimes you may even want to also get rid of the short distance problems, and then you're no longer doing analysis. You're really just doing algebra. You're back in this finite dimensional world that we started talking about at the beginning. Okay, so let me, but that's maybe then just to say a quick. Okay, so one way of motivating the whole story of Fourier, of the Fourier integral and the Fourier analysis is that we really, it's all about taking this story, which we know about, which has nice behavior, and then seeing what happens as L goes to infinity. And I think I wrote down, so let me just quickly maybe say one word about that. Okay, so for so if you, for general L, in other words, so we were, so far the formulas I wrote down for L is equal to 2 pi, but for an arbitrary L, you can rescale phi goes to what I call phi sub L, which is just rescale by multiplication by L over 2 pi. Now I'm worried that I've got that backwards. Anyway, then you're going to have your momentum operator P is equal to minus I H bar D T phi. If I use the rescaled phi, then it's going to have, will have eigenvalues 2 pi as 2 pi H bar over L times times n. So what happens is that if you work in this periodic boundary conditions on the circle, the thing which is going to have the interpretation as being the momenta are going to be things that are they're quantized. They come in as integers times some number, and this depends upon your units. And then what happens as L goes to infinity, the spacing of these eigenvalues goes to 0, and you get continuous possibilities. So as L goes to infinity, you get continuous possible mode. So from the physics point of view, you'll often see the advantage of going to these periodic boundary conditions and doing this, and putting the thing in a box, is that your possible momenta are, not just are your eigenfunctions, the momenta operator, going to be square integrable, but your possible momenta are just going to be labeled by these nice integers, and they're going to have to take these nice discrete values instead of being a problem in analysis caused by the momenta being continuous. So that's the story. But now the okay. So this is one way to motivate what you want to do, and so one way to study what I'm going to talk about now is to take the Fourier series case and then study the limit as L goes to infinity. But that's not the way. Anyway, so I'm not. That's one way to do all this. But what I'm going to do is just kind of write this down instead. And so we're going to try to work directly in the L is equal to infinity limit and define things there. So what we want to do is define. So this is, so everything I'm doing here I would call kind of the theory of Fourier series. And now I would say what we're going to do now is called the so-called Fourier transform. And now the idea is this, is that if you take the okay, so f So you're going to take functions on the real number lines, f of q. So f of q goes to, and there's various. Actually, maybe let me kind of just start using a psi, because these things are going to be our wave functions. So you've got psi of q, which is a function of r, goes to, often putting a tilde on the function means that I'm going to take a that's the Fourier transform, and this is now going to be, so this is a function of r, so q is an element of r, and this is going to be a function of p, where p is another real number line. And then you just define this this way. You integrate minus infinity to infinity, and then e to the psi of q, e to the minus I. I'm sorry, I was going to let me use this k for now. Q, and then 1 over square root of 2 pi. Okay, so this is going to be the basic definition we're going to use for how to do a Fourier transform. And what you should think of this as being a continuous analog of the formula that I wrote down for how you compute Fourier coefficients in terms of the function. There it said, well, you integrate over the circle the function times e to the minus I n q. Well, here we replaced n by we replace this discrete number value variable n by a continuous variable k. And I should say something. You also have to watch out that there are several different conventions for how you define this thing, and there are different conventions depending. You may put a basically there's no way to get around having some 2 pi somewhere, and I'm putting it here in a square root for something I'll explain in a minute. You could instead get rid of it here, by changing q. Anyway, by changing the normalization of q, you could get rid of it here and put it up here. Or if you like changing the normalization of k, you could put it there. So you have to watch out. Depending, everybody that you look at, you have to worry about which what convention they're using for the Fourier transform. This is the one I'm using, but I think sometimes you'll see physicists using this. Sometimes they'll use something different, but not always the same thing. Okay, but then now the basic theorem then is that a Fourier inversion and it says that, which says that you can recover psi from psi tilde with this formula. Infinity psi tilde. Okay. E to the I k q. Okay. Okay. And this is the analog of the formula that you had in the Fourier series case, where you said that you could recover a function by doing an infinite sum over the e to the inq times the psi times the ans. So this is kind of instead of an infinite sum, we have an integral now, and you get this. And this is so these are the standard. Anyway, so these are the kind of two crucial things we're going to use. The reason for putting this 1 over square root of 2 pi here was that then I could put the same thing here, and I didn't have to keep track. So often people will not put it here, but then they have to put a 1 over 2 pi here. But there's basically somehow, if what's going to happen is if you start with this and take the Fourier transform, anyway, if you start with a Fourier transform, do this, and then try and go back, you have to pick up a 2 pi somewhere, and that's going to, you have to put it somewhere. And here I'm just putting it symmetrically there. Okay, so this is the, anyway, so these are the basic. Now, so far I've avoided, okay. So I've avoided talking about the problem of what kind of functions. So let's see. So now let's. Anyway, so keep these in mind. And if you've seen, so these should be very familiar if you've ever seen people doing a Fourier transform before. If not, yeah, if not, you should look at these notes carefully. There's also these other notes that I mentioned in the file section. You can look for that, or find any good book on Fourier analysis. There's a long kind of story about you have to get used to trying to do trying to actually do these integrals and to understand what happens when you actually try and do these integrals and go from one kind of function to another. But let me just explain what the what happens to this problem of what kind of function. Okay, so what kind of function is psi and also psi tilde. So one question is, if you put some kind of condition on the functions you're going to look at, what kind of condition does that give you on the Fourier transform functions? And so one possibility is the is this psi over L2 R. So there's this possibility that I mentioned before, so one of the nice things about this, so besides having this nice, giving you the kind of physical interpretation you need if you try and use Born's rule, or if you actually want to work with any of its norm, you need its norm squared, or you need it to have finite inner products with other functions. This has a nice property. Psi tilde. And then so it said basically if you set things up well, the way that if you set this up correctly, you really can you can think of the Fourier transform as a unitary operator. So the Fourier transform F or F is a unitary operator. Or that takes L2 of R delta. Again, and depending upon how you set up your theory of integration, you have to be a little bit careful about exactly what you mean by L2. But when you take exactly what you mean when you take the Fourier transform, but ignoring technical problems, this is basically true that L2 of R is what you need for physical purposes, and it behaves very, very nicely under the Fourier transform. So that's all well and good. But it has the it has the problems that mentioned earlier. Okay, let's see. So the okay. So what do you do? Okay. So now the problems that so what we're going to do now for the rest of the class is try to tell you about the analysis that I want to do and in order to kind of get rid of these other problems, the problems that we had, and we're going to first. So first, what we're going to do is we're going to first let's get rid of. Let's address the problem of P H not being defined. Okay. Okay. So what you do, the way you do this is to restrict attention. Okay. So you have this problem that these L2 functions, in some sense, well, they have this problem that there's really nothing about their different. This condition says nothing about their differentiability, for instance. So an L2 function can be an arbitrarily, horribly non-differentiable gadget, and then so P is the derivative, and so you want to impose some kind of differentiability condition. So we're going to restrict attention to what are called Schwartz functions. Now I can never remember Schwartz as a T, I think, right? And so there's Schwartz functions, and so this is going to be, and I'll call this S. So this is S of R, and it's things that are in S of R and are going to be an L2. So these are going to. These are going to be square integral. That's going to be one of their properties. But they're going to have nice behavior under P. So what you want is you want them to have nice behavior under the derivative. And so in particular, you want if the function is in this class, if you take its derivative, you want it to stay in that class. Okay. And so. And then the other condition you want is you also want that you want this to also be true of the Fourier transform. You want the Fourier transform of a Schwartz function to also be a Schwartz function. So this picks out a standard condition which you use, which is this. So you define S of R is that functions of R with that they have all derivatives exist and then psi. That psi and all derivatives of psi fall off faster than any than one over polynomial. Yeah. That went over. Well, let's say went over. The end for the end. Okay. So what this so the condition that we're doing is we're saying first of all that it's that it's continuous. The function exists for all R. All of its derivatives exist. So it has nice. It's what's called this condition we're also called being C infinity. that big C0 means that you're continuous, C1 means you have one derivative, C2 means you have two derivatives, C infinity means you have all derivatives. But your extra problem is that you also kind of impose this condition that there can't be any problems at infinity by saying that the functions fall off, and they fall off also faster than any inverse than any power. So you want to, so typical examples are going to be polynomials, polynomial in Q times e to the minus Q squared. So you want something, you're going to have something which kind of causes exponential fall off, causes you fall off faster than any than any polynomial. And then if you multiply this by any polynomial, you're still going to have this exponential fall off. And these things are really have really nice properties that they have, all the derivatives of these things exist and are easy to deal with, etc. So if you want to kind of typically keep in mind what kind of functions we're talking about, these are the kinds of functions. These are the kinds of functions. So they're very restricted in that they've got kind of nice kind of polynomial behavior, nice derivatives and everything, and they've got really nice exponential fall off. Okay, so these are called so what we do with Schwarz functions, and then what you do is you then prove, and this and in some sense the definition of the Schwarz function, if you do it carefully, the whole point is to set up the definition in such a way that this is true, that if the Fourier transform that psi in S of R implies over. Okay, and vice versa, and the other. So just as L2 is a really nice condition to put on functions, because if you took the Fourier transform of an L2 function, you got an L2 function. Well, here this is also preserved by the Fourier transform. So if you try and use these nice Schwarz functions, and then if you take the Fourier transform, it will also be a Schwarz function. So you're living in this nice world of where you don't have to worry about whether the Fourier transform is taking you to something different, and so the Fourier transform doesn't take you out of the space, and the operator ddq doesn't take you out of the space. So the momentum and energy operators don't take you out of the space. So this is a very nice space. I mean, you still have okay. So let's just say you still have the problem that the space doesn't behave nicely. Anyway, so the eigenfunctions of translations are still not in this space. So you still have the problem that e to the ikq is not a Schwarz function. And so again, in the physics literature, often you'll see that the so I should say that these are what are called plane waves, or this kind of behavior in Q. If you then look at the solution to Schrodinger's equation, where that you'll get what's called a plane wave solution. Here, these things are often called wave packets. Okay. So the idea is that you anyway. So if you look at the physics literature, you'll often find that people start doing some calculation with these solutions describing free particles, and then realize they're getting into trouble, and they say, okay, well, wait a minute, we didn't really quite mean these. We actually meant something here. But then the problem is that this guy is not plane waves are not wave packets.
Good question.
Yeah.
So maybe I'm just missing something. It doesn't seem apparent that the short space is necessarily a subspace of L2. Do we normally talk about a short subspace of a function space, or do we talk about the short space being a subspace of L2 necessarily?
I think the way to think about L2 is that there's really, I mean, there's two things that can go wrong, and why you can things cannot be something is not going to be integrable. It's not going to have an L2 norm. I mean, something can go wrong locally that the function can be, like can be singular at some point or not, or yeah. I mean, but I guess the thing to say is that if any kind of function which is continuous, even which isn't blowing up anywhere and which is falling off fast enough at plus minus infinity, is an L2. Okay, so this the condition that the function exists at all points, that it's not actually blowing up, it's continuous, and the condition that it's that is falling off faster than any polynomial, that it's automatically an L2. Does that help?
Yeah. I forgot about the fact momentarily that smooth functions are all square integrable.
Yeah. So it's not, but that's the anyway. Yeah, that's just the general way to realize it, that the L2 is anyway. This is getting rid of local problems, saying that it's C infinity, and then the fall off thing is getting rid of the global problem. And those are the two things you have to worry about.
Thank you.
Okay. Let's see. Okay, so now the question is, how are we going to deal with this? Let me try to see. Okay, so here's where, and I guess that maybe I should have said, okay, let me, actually maybe before I get to distributions, let me just kind of say something quickly then about how you then use this. And this, so then the way you use the Fourier transform to solve the Schrodinger equation is this. So the Schrodinger equation was the equation was I don't know what it is, I h bar d dt. Let's write it this way, d dt, and now we've got some psi that depends on q and t. That it's going to have to be it's p squared over 2m, which is minus h bar squared over 2m p squared q squared psi qt. Okay, so the way you use Fourier analysis is you turn this into a problem about the Fourier transform. And so what you do, and I guess there's something, and I guess I should have told one of the let me not go through this argument, but you let's just say this, that you use the fact that the if you take d psi d q and you take the Fourier transform, of the derivative, that if you work out the formula for this guy and use integration by parts, you find that this guy is e to the I. Sorry, is ik of k is ik. Now I'm making into trouble here with my h bars. So as you'll see, I'm trying to go back and forth between using h bar, setting h bar equal to 1 and using it, and p, the physical momentum, is h bar times this k, which is the so you're dealing with functions e to the I k q. So in principle you can go you're going to have nice formulas with, in terms of k. If you want a momentum, you have to multiply by h bar. But the problem is I have to kind of consistently do this everywhere, and I'm very tempted at all points just to say that p at h bar is equal to 1 and p is equal to k. And maybe I better actually do this from now on in. So I won't have to kind of keep track of the h bars and where they go in the formulas for the Fourier transform. But anyway, sorry. So this is what this is this. I tell them. Finish that part, right? Yeah. So this is one of the great beauties of the Fourier transform, is that what it does is it changes the under Fourier transform the differentiation operator becomes just the multiplication operator. Okay, and this at kind of the level of thinking about the translation group, this is saying that so infinitesimal translations become multiplication. It's going to be. You can also show that an arbitrary. If you take a Fourier transform of a translated function, you get the original function multiplied by a phase. So that's the global version of this. But this is kind of the crucial thing that we're going to use. So whenever you want to talk about differential equations, if you have a differential equation for psi, what you can do by going to psi tilde, you can change the DDQs just to multiplication operators. So what you find then is that the so I better set h bar equal to 1, and then this guy then becomes I ddt psi tilde of k and t. So the t is just going along for the ride, but I Fourier transform in the q variable, and this is minus 1 over 2m times ik squared, and then psi tilde of k. And this equation you know how to solve. So this equation, so the solution is going to be, so here you just get a, oh, did I do this right? Yeah. Do the minus I. Why have I got a, oh, sorry, there's an I over here. Yeah, okay. Yeah, so this is right. So then you get a psi tilde of k and t is equal to, just the derivative of something is something times a constant. You know that the answer is always an exponential, so the answer is e to the minus I k squared over 2m and t times up to a constant, and times a constant, and the constant can be fixed by knowing what happens at t is equal to 0. So it's psi tilde of k 0. Okay. So this is your this is your initial condition. Okay, so if you want to solve Schrodinger's equation for any kind of any function that's describing what's going on with a free particle, you start with you have to start with by knowing what happens at t is equal to 0, and then so you start, for instance, with psi of q at 0, take its Fourier transform, multiply it by this guy, and then now you know what the Fourier transform of the solution is at all times, and so then you can go back and then inverse Fourier transform, and then find that psi of qt is 1 over square root of 2 pi infinity to infinity e to the minus I k squared over 2m t, and then this guy over k 0. Okay. So anyway, so you have this initial data, but then if you disintegrate this initial data against this function, you get the solution. Oh, sorry, what did I do? Sorry. Now there's an e to the ikq. So it's just the Fourier transform, and just the inverse Fourier transform of this guy. Okay, so this is one of the nice motivations for Fourier analysis is just that it just solves differential equations like this very nicely. Okay, so now for the last 15 minutes, let me kind of tell you about. So all of this works perfectly well for Schwartz functions. So if you start off with psi, a nice Schwartz function at time 0, then it's Fourier transform at the initial. This guy is also a Schwartz function. This kind of Fourier transform, then multiplying by this guy, it's still a Schwartz function. This Fourier transform is still a Schwartz function. So everybody's at all times a nice Schwartz function, and you're perfectly happy. But your problem is that you don't. What about this? Doesn't allow you to talk about this case where psi. So what about? Let's say psi. Let's take say psi of q at time 0 is equal to e to the ikq. And so you would like to be able to talk about solutions like this. These are the things which behave nicely in our translations, and these are the simplest plane wave solutions. But they don't fit it at all into this in this formalism we've set up. But because you can't integrate them, you can't take their Fourier transform doesn't seem to make any. You can't. Anyway, they just don't have any of the properties you need. In particular, they don't have. If you take the Fourier transform of this thing, if you try to take the Fourier transform of this thing, you quickly find that it's not a function. I mean, the Fourier transform at 0 is going to be infinite. Okay, so what do you do? So this is the theory of distribution. So distributions. So the idea. Okay. Well, remember. So one of the nice things about L2 of R was that if you took if you ask in some sense, what's the dual space? What are the linear functionals on L2? If you use the fact that you can use this inner product, whenever you have an inner product on a space, you can use the inner product to give you to define the dual. And so this has dual space. Okay. So this is one of the nice properties of this. What we're going to do is consider as prime of R, which is the dual space, so what we're going to do is that instead of thinking about functions, so this is going to be some space of linear functionals on Schwartz functions. And so the idea, anyways, this is the general idea. And so the main problem then is to kind of how to work out this philosophy and how to but maybe just as kind of a general matter of philosophy. This was kind of one of the great innovations of mathematical analysis, and starting in the 1950s due to Schwartz, is to realize that a lot of the problems that people had always traditionally had about dealing with dealing with problems in analysis was always that you were often working with much too restrictive a notion of what a function was, and your typical problem was that what was exactly the kind of problem that we're seeing here, that you don't the notion of function you were working with, if you took Fourier transforms, it was no longer a function. So you needed to generalize the notion of functions. So these are examples of, well, these are generalized functions. So the idea is to work with some more general objects, and what you find is that let me just kind of first say kind of what kind of one of the bottom lines is here, and then I'll start working out a little bit more of the details of how you do this. Because you find that okay, so we know that Schwartz functions are in L2 are L2, and but they're much more restrictive. They're in some sense a small subspace of L2. But then what we find that any L2 function can be thought of as an element of the dual space. You basically can, if something is in L2, you can integrate it against something against things in here, and that gives you a linear functional on this. So here, anyway, so these lie in here, but these guys give you examples of linear functionals. Or so here. Well, let me just say it here that to a function in here, maybe a better. So here f goes to the integral infinity to infinity of f against dq. Okay. So if you think of functions, to any function, you're going to get a linear functional on the Schwartz functions by taking the function and saying I want to integrate it against the Schwartz function, and if this guy's an L2 and this guy's Schwartz, this is going to make sense. Okay, so you can generate so these guys fit nicely into this. You can think of these guys as examples of linear functionals through this formula. And then what happens is that the nice thing is that if you take the Fourier transform, so and I'll sometimes write the Fourier transform this way. So the Fourier transform takes this to this, it takes this to this, and again you're here, and it's also going to take this to this. Okay, so I'll write over here, but here. So the general idea is that we're going to solve our second problem by kind of bootstrapping ourselves from these guys and saying these guys have really nice properties. But what we can do is we can go to general. We can look at the dual space to this space to this space and work with these guys, and then. But because these guys are just linear functionals on these guys, they inherit a lot of the nice properties of these guys are inherited by these guys. In particular, the fact that Fourier transform takes you from a Schwartz function to a Schwartz function means it takes you from this kind of distribution to this kind of distribution. So I'll say a bit more about this, but this is the overall picture. So the picture is that the way we're going to solve our problem of, so let's write this down. But it's a bit easier. Okay, so this solves. Let's see. Oh, and maybe just something about terminology that so S prime of R, these are called tempered distributions. Okay, so if you look at so if you could create your distributions by taking the dual of the Schwartz functions, they're called tempered distributions. There are other notions of what a distribution is, given by looking at different not Schwartz, by starting with Schwartz, not starting with Schwartz functions, for instance, but for instance starting with functions that are C infinity and that are zero outside of some compact set. And so when somebody says distribution, you can't be, you have to watch out what they're saying. When I say distribution, I'm going to be these guys, because these are the ones that have really nice properties under Fourier transform. But then, so then e to the I kq gets interpreted as not as a function, but as psi. It's the thing that takes a Schwartz function to from minus infinity to infinity, e to the I kq psi of q. But this is just the well, this is just psi till the, I guess there's maybe there's a minus sign here. Anyway, so what this is, okay. So what we're going to do is we're going to say that, okay, we now have a universe of objects which includes the things that we want, and includes these plane waves physically, which are also these things that are nice, behave nicely under translation. And but the point is that these guys, but the linear functional, but you're not supposed to think of this guy so much as a function. You're supposed to think of him as something that you can feed nicely behaved Schwartz functions to, and then get a number. So here I've written down the linear functional. So this will sometimes write as well. So you're thinking of this as a linear functional, and you're feeding it phi, and you're getting a number. I guess these are complex. You're getting a number. So this is a linear functional from here to C, and that's how you're supposed to think of it. But you can think of what. So then what happens though? The Fourier transform. Well, the other crucial example of an element of S prime of R is what I'll call the it is a linear functional that takes psi S of R goes to psi of A. Okay. So this is just evaluation at A. Okay. So we're just taking a function and we're evaluating it at a point. Well, that's a linear functional on functions. Okay. And so I'll have to kind of wrap this up now, but the this language of linear functional allows us to generalize functions to things which include this guy. And what you often do is you often use you often try as much as possible and use the language of functions to talk about distributions. So then this is then what is called the this element of f prime of r, this generalized function is often called written delta of q minus a, and called the Dirac delta function. Okay, so when people talk about the delta function, and I think most physics books pretty much have to do this at some point, they mean something which is not actually a function, but it's a linear functional on Schwartz functions, which is given by this. And so then and what you use that so what you do is you generalize as the integral of f phi dq for that this was anyway. This is the thing that I told you about before, that for any function you could create a linear functional this way to infinity. Instead of functions, you can put this symbol in there, and then phi dq, and you still get something meaningful. You get evaluation at A. Okay, so this is going to be so the way you're going to work with distributions often is you're going to kind of treat them as if they were functions, but what's actually going to make sense is not the value of the function, but what happens if you integrate it against well-behaved functions. Okay. And so that's what's and the delta function is kind of a perfect example. There's another. Maybe I should also quickly say there's another point of view is to realize as distributions as limits. So there's another way you can kind of justify all these manipulations, is that whenever you're trying to talk about some distribution, to find some to realize it in a certain specific way as a limit of well-behaved functions, and in this example, the delta function is going to be a limit of delta of q minus a is going to be some limit. I don't know, as alpha goes to 0 of e to the minus q minus a squared over alpha. Okay. And then you have to put some kind of type some constant depending on alpha. But you can so you can realize, you can think of this guy as he is the guy you get by looking at some kind of nice Gaussians and then taking the limit as alpha goes to 0, and then this is then something that becomes infinitely peaked at A. And the problem is that in this limit, as alpha goes to 0, what's happening is that the function is going to 0 everywhere except A, where it's going to infinity, and it's not, the limit is no longer a function, but the limit is a distribution. Okay, so maybe I guess I better stop there. There's a lot more in the notes about distributions. There's also even more in the notes from my Fourier analysis class that I uploaded to Courseworks. Maybe just a warning about the last section of the chapter. This may or may not have been a good. This is something that I kind of stuck in later because I'm gonna want to talk about. I'm gonna want to use some of this stuff later. But again, I think the best advice for now is don't. If you find what's going on in section 11.5 confusing, it's natural. Don't worry about it for now. We're not gonna do that now. But are there any questions about any of this stuff right now? And so I haven't really worked out any much in the way of examples or done much in the way of calculations, but I'm hoping that, especially if you look at any physics book, the idea is that what I tried to tell you here was to try to kind of give you the right mathematical framework for actually, making statements about all of these objects that make sense. That you'll find, I mean, the typical problem with the physics calculations is that they don't really have a good language for what this delta function is. And so they'll start using it and try to develop some of its properties, but they don't really have any kind of precise language for what exactly they're talking about. And then the other problem is that without knowing what kind of functions you're talking about, very often the calculations and manipulations you're doing, you can easily run into trouble if you start applying something to the wrong kind of function where it's not going to work. But at least I've kind of tried to give you a framework of how to actually do the stuff legitimately, though. Even though anyway, to actually prove theorems about this and to work out the details of this, you need to do much more work, which I don't want to really have time for in this class. But we'll see. This is the framework we're going to be working in at the anyway. So we are going to need sometimes to, very often when we're talking about wave functions, or we're talking that they often are going to be well, anyway, we're going to start when we're talking about things like plane wave solutions. You should realize we are talking about distributional solutions. Okay. Any other questions? Any questions for now? Okay, so let me so next on Thursday we'll do some more about the free particle. I mean, the other thing which you can get out of the Fourier transform is that you can Fourier transform back and forth between momenta and position. So besides just having a momentum operator, you can take the Fourier transform and get a position operator. So so next on Thursday we can actually finally start talking about not just the momentum of particles but about their position. Okay. And if you have any more questions, just I'll end this now. But please do come back in a minute to the other Zoom session. Okay. Bye for now.
Thank you.
Bye.